Hello, once again, this is part 4 of a reaction to a planetary core and surface temperatures, a paper by Douglas J. Cotton, and published in SSRN Electronic Journal, January 2013. In the last two videos, I struggled to get through the first 3 paragraphs of section 2. And I'm still going to struggle to get through these because I want to see if I can do yet a better job of describing the model which Douglas Cotton is describing here. Let me show you the last best effort that I made. The last best effort that I made was that nitrogen and oxygen were insulating materials and carbon dioxide was a radiating material. And I was comparing that to the standard greenhouse gas model, where oxygen and nitrogen are both transparent, but carbon dioxide both insulates and radiates. And I wanted to describe what that transparency means in terms of a couple of things. That transparency means that they are perfect radiative conductors. Like any radiation going through, it's transparent, so the radiation just goes right through, and they're perfect radiative conductors. On the other hand, they're also kind of like almost perfect conductive insulators, because because the heat won't go through the oxygen and nitrogen. When you put your hand next to something, you have to actually go all the way up to it and touch it before the heat can transfer to your fingers. So I want to come back to what his version of things is, and his focus is that conductive insulator part. He doesn't really discuss the radiation part. He just says that these are insulators. So he doesn't really acknowledge that they are radiative conductors, that light just goes right through them. Instead, he wants to focus on the insulating part and just describe them as insulators. And then he's also describing carbon dioxide as a radiator. And so I want to just kind of like describe this phenomenon in the best way I can. Just imagining that heat is transferred from the planet's surface to the oxygen and nitrogen particles by conduction, by just regular conduction. And then when the heat passes to the carbon dioxide molecules, then the carbon dioxide can radiate a photon straight into outer space, and that results in the cooling of the planet. That's the way he's thinking of it, and he's just kind of misses the part where the oxygen and nitrogen don't block the radiation at all. But he's saying that the carbon dioxide has some kind of special quality where it alone has the capacity to radiate the energy into outer space. So I don't want to poo-poo his hypothesis, but that basically is what it is. That he's just saying that the oxygen and nitrogen are perfect insulators, so they don't radiate the energy into space. But the carbon dioxide, it actually has the ability to radiate the energy out into space. So you can decide for yourself whether that argument makes sense, but I would also encourage you to recognize that my version of oxygen and nitrogen are transparent, so this carbon dioxide doesn't have some special capability of radiating the energy into space. It's actually the oxygen and nitrogen that have the special ability of allowing the radiation to pass into space, while the carbon dioxide actually blocks it. So we'll move on now and read a bit more of the paper. It says radiation from a cooler region of the atmosphere affects radiative cooling of the surface because it provides electromagnetic energy for some quota of radiation which the surface is emitting. So radiation from here, the cool part of the atmosphere, provides some quota of the radiation from here. That works for in both models. You can say the radiation from here provides some quota of the radiation from here, but actually, in this model, everything is eventually passed through. 100% comes in, 100% goes out. So the quota is 1-to-1 in this version. The top surface, each layer, 100% is sent out, 100% absorbed by this layer, 100% is sent out, 100% absorbed, 100%, 100%, 100%, 100%. Each layer both absorbs and emits 100% of the radiation. And it's just that this layer happens to actually emit, this final layer at the very top surface actually emits more radiation than came in. And that amount that comes out has the same amount of energy as the visible light energy that was absorbed by the planet. I think I'm struggling here because I really need to I need to go full into his model of things before, like right now I'm like going sentence by sentence and going, okay, this is what his sentence means in the context of such and such a model. But it's almost impossible to be switching back and forth at this point, like going, okay, this is what it means in the context of his model, but what would it mean in the context of the actual greenhouse gas model? It's practically impossible at this point to go back to the actual greenhouse gas model and interpret what he's saying. I mean, it's practically meaningless in terms of the actual greenhouse gas model. Okay, here though he says this is the NASA energy budget diagram, which comes from a website, objectivistindividualist.blogspot.com. NASA finally produces realistic energy. One thing we want to immediately check is that the incoming solar radiation and the outgoing radiation is the same, and I think this matches that because this 6 plus 20 plus 4 is 30, 64 plus 6 is 70, 30 plus 70 is 100. So we have 100% in, 100% out. So that's pretty fundamental. If you want the incoming amount of energy equal to the outgoing amount of energy. So it looks like 6%, 20%, and 4% are reflected off of various surfaces. 16% gets absorbed by the atmosphere and is re-emitted in infrared light, basically infrared light from the atmosphere. 3% is absorbed by the clouds and is re-emitted as infrared light from the clouds. And 51% of it is absorbed by land and oceans and re-emitted as infrared light from the land and oceans. And then there's these other paths that it takes. So some of it was absorbed by the atmosphere, but of that 16% that was absorbed by the atmosphere, 15% of it Or is it the other way around? Okay. Huh. There's no arrow here, but let's say the arrow is going up. Of the, I guess this would be 15 plus 6% is 21%. That is 23%. 23% carried to clouds and atmosphere by latent heat in the water vapor. All right. Here is another diagram of this Earth's energy budget. I do not like this graph. I do not like it at all. But the reason I don't like it is because these numbers, 340.4 minus 77 minus 22.9 minus 239.9, come out to be 0.6, and they give you this net absorbed, but it says 0, and I'm like looking at this, it's like 0.6 watts per meter squared. The idea that the ground is absorbing 0.6 watts per meter squared is basically saying that it is, well, let's just say over the course of a day, there would be a significant, you'd notice a significant amount of warming if that were the case. But then it says all values are fluxes in watts per meter squared and are average values based on 10 years of data. Actually, before I dismiss that number out of hand, though, let us think about, let's take a cubic meter of water, 1 meter and 1 meter and 1 meter, and think about let's say this is 1 meter of water at 15 degrees Celsius, and figure out how long it would take to raise that cubic meter of water to 16 degrees Celsius at 0.6 joules per meter squared per second, which is 0.6 watts per meter squared. And see, just to get an idea of what that 0.6 joules per meter squared actually represents. Okay, the specific heat of water is 4,186 joules per kilogram per degree Celsius. So what do we need to do here? Okay, it's coming back to me. The heat is mc delta T. So we get a rate of temperature change of 1.433 times 10 to the negative 7th degrees Celsius per second, which comes out to be about 4.52 degrees Celsius per year. So if you really think about that in terms of everything, instead of just the water 1 meter deep, think about the water all the way down to the bottom of the ocean, and maybe the ground. I don't know what the coefficient of the specific heat of the mantle of the Earth is, but you'd also use like the specific heat of the mantle of the Earth to figure out how much heat is absorbed by it. So if that 0.6 joules per second is accurate, they would have to be accounting for the heating of just the landscape and the oceans as well. Because I know that the actual temperature, the temperature of the Earth over the last 10 years hasn't gone up. This would be 45.2 degrees Celsius in the last 10 years. So we know that it's not that much. We know it's closer to, like, at best maybe half a degree Celsius per year. So they would have to be accounting for a very deep thing to be saying that the atmosphere is absorbing 0.6 joules per meter squared per second. I also really don't think much of the conceptualization, the way that things are conceptualized here. The idea of back radiation, that's really not a useful way of thinking of it. the emission and back radiation, no, it's conduction. It's just simple the conduction of heat from the ground to the top of the atmosphere. Use that. That is a that's a useful construction because it shows how it basically describes it as a simple concept as something providing extra. Um, you're adding layers of insulation when you add the when you add more carbon dioxide to the concentration of the atmosphere. This idea, I guess it might be a bit useful. Maybe if you want to, maybe I suppose there might be some additional benefit to the modeling by thinking of it in this way. But since ultimately you're going to be this figure is hard to justify really without a lot of extra explanation, like exactly like basically absorbed by what are you talking about? Absorbed by how deep are you going into the ground when you're talking about how where this energy is being absorbed, because that energy is being absorbed by a really large region of rock and ocean and everything else like that. Okay, now let's look at how he his name how he is interpreting this graph. He says, you will see that only 15% of the original incoming solar energy is transferred by radiation, which is absorbed by the atmosphere. So there's only one place in this graph that has that number, 15%. It says radiation absorbed by the atmosphere. And I think if I follow these arrows correctly, this is incoming radiation 100% is absorbed by land and oceans. Then you follow up the red graph here. It doesn't tell you how much is coming through here, but it's 20, let's see, 7% here, 23% here, so this would have to be the leftover of 51 minus 23 minus 7, which would be, so we have 21% coming up here, and then 21% divides into 15% that comes this way and gets absorbed by the atmosphere, and 6% goes directly to space. So he says only 15% of the original incoming solar energy is transferred by radiation, which is absorbed by the atmosphere. No, 64% of it totally is radiated from space, from the clouds and atmosphere. Let's see. Then he says, whereas twice as much is transferred by non-radiative processes. Okay, conduction and rising air, 7%, and 23% by latent heat in water vapor. Okay, he kind of says, one thing though he says here, energy stored in water vapor, but you'll notice it doesn't stay stored in water vapor. It reaches the clouds, and then probably about the same time that the clouds rain, then about that same time they also maybe emit photons that are radiated into space, probably in the infrared spectrum out into space. So that's an interesting idea, that that cooling process, that when when clouds rain, maybe send down a droplet of water while also sending out photons in the infrared spectrum as they cool. Will also be noted that 19% of the sun's incident radiation is absorbed by the atmosphere and clouds. So 19%, so yeah, 16% here and 3% here is absorbed. And actually, don't just count that. Count this 6%, 20%. So 26% plus 16 and 3 give you 45% altogether. So yeah, technically it looks like about 45% of the sun's rays never actually reach the surface of the Earth. And it says more than 15%, which is, okay, I'll read that for a second. It says, yet some greenhouse proponents say the atmosphere is transparent to solar radiation. And I would say, yes, I am a guilty party. The fact that let's see, 45%, 55% of the visible light makes it through to the Earth's surface. 55%, yeah, 55% is basically transparent. I would go with that. Can also be very angle dependent. So I would say my guess is that if the sun is up here, then coming down there that way, that the atmosphere would be pretty much transparent. And if you came this way, for instance, the atmosphere would remove a whole, just would be almost, okay, but it's going to be very, very reflective in the blue, range, because when you come through, when you come down and the light hits that surface, then, well, I'm not sure where it comes from, but the light hits that surface and then just bounces around a whole lot, and the blue light bounces around a whole lot, and eventually what gets to your eye is that the whole sky looks blue, because none of the blue light has made a direct passage to your eye. Almost all of it has reflected, gone different directions, so that the whole sky looks blue. And then when you get down here and you're looking at the sun on the horizon, you get the blue reflection over here, but over here it's like turns all red and orange. I'm not sure exactly what causes that red and orange effect to happen. Another thing that happens, if you're lucky enough to see the sun right at sunset on a real clear night, looking over the ocean, you get something called a green flash. And the green flash has to do with a particular emission line of the nitrogen or the oxygen spectrum. I don't remember whether it's nitrogen or oxygen, but there's a green emission line, but it's a green emission line that just like has no phosphorescence, practically no phosphorescence at all. So it has that green line, but it lasts for such a short time that you can't see it except when the sun is viewed head on, and you can't see it at all because, well, you can't really look at the sun head on. So the only time you can see it is right after the sun goes over the horizon. But yeah, I am guilty of saying that the atmosphere is transparent. But yeah, actually, there's reflected by the atmosphere 6%. That 6% reflected by the atmosphere, that turns into blue light. Mostly that turns into the blue light that we usually call the sky. And actually, you might consider that blue light absorbed by the atmosphere too, because that light just kind of keeps bouncing around. That blue light bounces around and eventually comes to your eyes. Absorbed by the clouds. Yeah, sure. That usually, you see that come out of the clouds. I'm more accustomed to the light that is reflected off the clouds because that's what I see. You see the white clouds. But absorbed by the clouds. I'm not sure what color light comes out of clouds when it's re-emitted from clouds um, rather than being just reflection. In any case, he's comparing that 15%, this 16, what is it? He's comparing this 19%, 16 plus 3, to this 15%, this orange line here. But I would probably compare that 15%, well, I would compare this 51%. No, this 51 plus 4. 51 plus 4 is 55%. And compare that, because that 51 plus 4 made it all the way to the ground. And compare it to how much of this came directly from the ground. How much of this came directly from the ground and made it into space? 6%. So 55 versus 6. That's the comparison of the transparency. 55% came in. It's 55% of the visible light made it all the way to the ground. 6% of the infrared light made it all the way into space.